Hello and welcome to this tutorial on advanced surfacing for SAE Aero Design and Design Build Fly aircraft. So aircraft are a mix of free-flowing surfaces for aerodynamics like this wing and like this wing root fillet, and also they have design intent that is exacting dimensions and angles and planes, like for instance for the internal structure and the way it interacts with the outer surface. And for instance, for requirements, like take a look at, in this case, the rules of the 2017 regular class allowed for 144 inches. And even with all that curvature and different things going on in the design, and you want to meet that design requirement. So one way to meet all of those mixed design intents, a good way to do that is with top-level assembly design using surfacing. So we're going to take an in-depth tour of the surfacing on this aircraft, and maybe you'll get some inspiration for top-down assembly modeling techniques to get what you're looking for in your designs. So we're going to start off by taking a look at the top-level assembly geometry. For instance, this dihedral layout gives top-level design intent information right from the top-level assembly for instance, the 5 degrees of dihedral that the wing follows along, this 8 inches of winglet, and where we want the winglet tip to end up, and also the positioning of the wing, how much lower it is than, for instance, the passengers, and it allows for sort of efficient changes in the design as you're working. So we're going to take a look at the top level assembly information, and also the surfacing for the wing, the winglet, and also the fuselage and the wing root fillet, the fairing. That's an area where there's a smoothing of the interaction between the wing coming in and the fuselage, both in terms of the aerodynamics, and also this area is sort of often the most complicated portion of any aircraft, just because it's also where the highest loads are, and where loads are coming in from the direction of the wing and also from the fuselage. So we're also going to take a look at how the surfacing was done in this aircraft with the design intent of, this one is a low wing configuration with the design intent of having the payload and the keel beam just beneath the passengers. This was the 2017 tennis ball passengers from the SAE Aero Design competition. Now, so this aircraft has a elliptical planform. It has these winglets. This involved wing root fairings on a low wing configuration, and so those aren't features that are required for an SAE aircraft. Of course, each of those adds a bit of performance, but before going with a top-down assembly with surfacing with as many complications as this, I would make sure to be familiar with bottom-up assemblies of rectangular planform aircraft, then also assemblies of trapezoidal planformed aircraft. So one of the main reasons for added difficulty with curved planform wings over straight tapered wings is that wings such as this elliptical one have compound curvature. So in this direction they have curvature, and then if we look straight down, let's say one of these stringers, we can see that in that direction they have curvature too. Now, that's in contrast to, if we look at, so let's look at a straight tapered wing. Now, if we take a look at straight tapered wings, they do clearly have curvature along the direction of the airflow, but we can always find, regardless of their taper or washout, we can find along the OML of the surface, we can find straight lines that don't curve. For instance, if we look down the stringers. Now they have to be arranged at a certain angle for them to be straight, but for manufacturing and design that is usually simpler. Now coming back to this aircraft, I want to remark that just because something is more difficult doesn't necessarily make it better or higher performing. But one thing that is for sure is that expanding our modeling skills is an advantage to help us come up with and model ideas for any of our designs. So with that in mind, let's get started. First, we're going to take a look at the surfacing of the wing coming down from the dihedral layout. So let's hide all these sub-assemblies that have been started, and also even the generating OML. So now we just have the top level assembly wireframe, with the first sketch being the dihedral layout, which sort of sets the scene for where the wings are going to be, where the winglet's going to be. So the wing follows this 5 degrees dihedral, and the winglet, the tip point ends 8 inches up, and we're making sure that that tip point of the winglet is 72 inches out, so our wingspan can be 144 from the top view. Now, from that is where we can start to look at the wing. So the wing, let's take a look in the OML. So there's some folders in it, and it's all the same part, but just organized into folders of the features for each segment of the aircraft surfacing. So we'll take a look in the wing. Let's actually just expand each of these so that as we roll it back, we can still see what gets hidden inside these features here. So let's roll it back right to its start. And at that point, all we've got is a root plane that just takes its information from a point on the dihedral layout and the dihedral layout line. We have the root angle of incidence. Well, actually the first one that I put in is this root airfoil. So all that is the airfoil that has its midpoint of a certain percentage of its chord pierced to the dihedral layout line, and then we make sure that it has an angle of incidence and a chord length, and that's pretty much it for the root airfoil. Then, so we have the root angle of incidence, which is just a line along that airfoil, the chord. The tip, which is in the tip plane, and it has less angle of attack than the root. The root had 3 degrees, this has 1.5. And this we'll get to in a minute, this sort of seemingly arbitrary offset from where the dihedral line ends, because the dihedral line, it went through the midpoint of a certain percentage chord of this airfoil here, but at the tip of an elliptical wing there is no airfoil. There's just a point. For now, I just have. We'll see where this one comes from in a minute. That 0.77. So we just have the root airfoil, the tip airfoil. Then, if we go down a bit, so I've generated a surface from those two lines. So if we visualize it, it's really just a surface that is coming from the angle of incidence of 3 degrees here and the 1.5 degrees here. So it's just sort of a plane that's twisted a bit for the washout. So let's hide that again. So then there's the planform, which is on created a plane for the planform, which comes from the root angle of incidence. And the planform itself it's an elliptical, two partial ellipses from the leading edge portion that I think is a 30% chord, I think, ahead of this point, and then the trailing edge portion, and some markup geometry for where, for instance, the ailerons will be and things like that. So we also have just this plane to reference that no part of the wing can exceed this plane, even though some of the planform sticks out beyond this plane here, because that's beyond 72 inches of this portion. So at the end with our winglet, this will curve up and not go beyond that point. So then the planform within the plane of the planform gets extruded as a surface. So then what we have is two surfaces. One that's the planform and another that is this twisted plane. And so the planform is being extruded at this 3 degrees back and 5 degrees up dihedral, and this twisted plane is coming along as we saw before, and where they intersect, that's going to be our trailing and leading edges. So what these are, if we hide this and hide that, what these are is the intersection between those two surfaces, and that becomes our leading and trailing edges that have that washout built into them. So then we can do a boundary surface of up until where the winglet starts. So that involves the root airfoil, the tip airfoil, and so the tip airfoil was, where was that put? That was put onto the tip airfoil plane. This one here, which just referred to part of the planform, where it knows the aileron ends, and I think it's a 1/4 of an inch past where the aileron ends. So, and that's a slightly different airfoil. I think this is the Epler 422 I think I used here, and this one is just slightly less cambered. So that's kind of like a aerodynamic washout also. And I'm not an aerodynamicist, so I don't know if those numbers actually make sense to do a 1.5 degree washout and also transition from those two airfoils. But yeah, the intent of this video is the design aspect of it. So then after that, so that's pretty much it for the inboard portion of the wing that's not the winglet. So the winglet itself, so I have a sketch here to locate where it's going to be. So the concept of the winglet was that, so I made a plane where the tip airfoil is at its leading edge, and also one where at its trailing edge, and those are each referencing the angle of attack at the point of the trailing edge, or at the point of the tip airfoil. And so there's a curve that I made coming out of each of those points in those planes. So they're not exactly the same, but they come out from the trailing and leading edges there. And so for instance, this one is forced to have a 3 degrees radius of curvature, tangent, and it's piercing, or coincident to this point, which is in the winglet locating sketch. So we'll take a look at that. So then the trailing curve is similar, but I couldn't force it to have a certain radius because it's meeting a slightly lower point. So we'll see why that is. So if we take a look at in the locating sketch, so these lines here are parallel to the line that this line here in the tip airfoil. So that's the direction that it's perpendicular to the planes coming out of these 2 points. So also, so this point here from the dihedral is not exactly where the tip of the winglet is going to end up, just because it's being extruded downward slightly also. So this point here is actually where the winglet tip is going to be. Right there. Because this here I made sure to be parallel to just something that's actually horizontal in the whole aircraft. So if we take a look at this surface now, so this surface goes through from the leading edge curve to the trailing edge curve, and we're making sure that it passes through this point here. so that we have the tip airfoil, and these again are pretty much the same concept as the leading and trailing edges before, but they're intersecting between the planform and this this sort of takes the place of that twisting plane, the twisting dihedral plane. This takes the place of that for the winglet. It's sort of a slightly twisting, curved plane. So these are the intersection. The way you do that is it's in intersection curve. So you can select, for instance, this surface and this surface, and then go to intersection curve. So then there's a couple more sketches in here just for defining the shape. So there's the tip airfoil, the winglet tip point, which is just a point where those 3D curves that are the intersection curves meet. So we just need a point for the loft where it ends, and that's the tip point, or the winglet tip point. Then we have those two curves, and just an upper profile just to help it define its shape. This here, I think, just required some tangencies and sort of some design intent of how thick you want the end to be, because you don't want it to be such a knife edge. You need it to end with a bit of thickness to be able to manufacture that. And that's pretty much it for the wing and the winglet. So if we hide this surface again, looks like it. And you can see it comes to this point, not the point in the dihedral layout here, just because it's being well, one of the guiding surfaces was extruded in a sloping down plane down these lines here. But to get it to reach its full 72-inch span, it's just a bit higher than that along here. So that's the wing. Then we can take a look at the fuselage. So at this point, they're completely separate. They're just approximately near each other, and the way that they're near each other is controlled by the dihedral layout. Sort of, if we were to change the dimensions in the dihedral layout, we can easily move the wing up and down or inwards and outwards at this point. So the fuselage will open up to these features too. This one gets a bit awkward to roll back just because in a fuselage, you're using the same, if we were to call each of these segments of the fuselage bays, then each neighboring bay uses the same frame sketch for the forwards part and the aft part. So if I were to do this again, I would probably make we can take a look at, there's a plane for each transition where the fuselage makes a cross-sectional change. And I would probably make all those sketches up here, and then for the sketches that are actually in the features, I think I would just copy or convert entity them in to to unnamed sketches that are used in the features, just because then you have your frame cross-section sketches at the top, and if you were to change those, that propagates through the entire tree. Whereas here, I mean, one of the sketches that's in the aft, in this bay is also used in the forward bay. So it just, with rolling back, it gets a little, you just have to open your features up to make sure you can see everything. But yeah, so we have, for instance, cross-sectional shape, and those are defined from some measurements and from where the passengers are, just to clear them. Same thing here. So this one is, the top half is identical, but the bottom half is a bit lower according to these top and bottom curves, which are if we go down. So that's what's controlling it here, is some curvature. So generally don't want things to change curvature too quick. So like, for instance, you can make sure they're collinear. One of these frames might be driving the angle that this comes down at, but then we want to make sure that it continues at the same angle, so that ends up collinear, and then the point gets used to create that frame. So just the design intent was to keep things smooth, and it's up to you to work out what drives what. I mean, I liked working from the front backwards, but so yeah, so we have then for the nose cone, this sort of has a lot of curvature in it, so I did it in two parts and then mirrored it. And that's pretty typical, just bottom, that's coming from the bottom curves sketch, and then a right, and also a top that makes sure it clears the last passenger that's going to be there. Then some knitting, these, mirroring of it, and knitting of the mirror together, so it's one big cone in the front. Then, okay, yeah, this was a different design that was unused, so we can hide that. So then at the point where we get to near where the wing starts, here's where I wanted the fuselage to actually curve inwards. I wanted the transition from the 3 passengers wide to the 2 passengers wide. I wanted that to be a smooth transition. So I just did a tangent. That's not actually the one that's used. The one that gets used is, if we go to here. So there's a 2-passenger bay, and here's the ones that are used. So those are just so a tangent to the straight part of the fuselage and a tangent to the straight part of the fuselage after it, and then 2 tangent lines that are forced to be equal length. I find that makes it a pretty smooth transition. So I wanted it to slowly get narrower over where the wing is starting to come in, and this leaves a lot of room for structure and things on either side here. So then just a bay that continues to accommodate the too wide, but continually goes upwards here from these two. Then sort of a sketch to find where the empennage is converging to, and a tail cone that follows that and transforms sort of this filleted rectangle to a circle. Then, and this is where, so this is another sort of the same thing as the positioning of the wing sketch or the dihedral sketch at the top level assembly. This is one sketch that positions where the empennage is going to be at, both with height and some measurements relative to where the passengers stop. So then this is just for reference for the hatch for later, for where the surface needs to be, well, there needs to be a different removable surface on top for the passengers. And that's it for the fuselage. So for the VFin and the HStab, those are a bit simpler. Those are just in referencing from the empennage locating sketch in the fuselage, and yeah, just a planform and the root airfoil. Same thing as this wing, but less complicated here because there's no washout or anything like that. No need for a 3D intersection curve, just straight from the planform make the boundary surface or the loft here. And the HStab, it does have a cambered airfoil. Here it's an upside down cambered, lightly cambered airfoil, and similar to the wing, we have a visualize a washout plane. I think just washed out 1 degree, I think, and then a planform for the surface for the planform, and then some intersection curves from the root airfoil to the tip point. That's the HStab. And it gets a elevator split line too. And the VFin gets a rudder split line. Just for, those aren't used here, they're just sort of a top level reference for later. And then there's the wing root fillet. Now for the wing root fillet, there are lots of ways you could blend the surfacing between the wing and the fuselage. It's going to depend a lot on the shape of your wing and your fuselage, the camber of the airfoil, and the angle of incidence of the wing, and also whether it's a low wing or a mid wing or a high wing, especially for where that trailing edge ends up, how much lower it ends up than the fuselage. Now, I'm not an aerodynamicist, so I can't give advice for which type of fairing to go for a given aircraft, but we can look at other designs that are established out there, like for instance for this one here, what I was sort of emulating was the one found on the Spitfire, so that's kind of like a small radius towards the leading edge and then the radius gets larger and larger towards the trailing edge. And it is a low wing, so there's the trailing edge is a bit lower than the fuselage, and they kind of loft the trailing edge back out to the fuselage. So that's one of them, but I mean, there's definitely others. I mean, this is another plane with an elliptical wing. This is a Heinkel 70, and you can even see that near the root they decrease the chord length. So this fairing is much smaller. It kind of has it looks like the radius is about the same along most of the length of it. So what I was going for here was sort of increasing the radius from the leading edge towards the trailing edge, and kind of swooping that air underneath to meet the air that's already going underneath the fuselage. And this is the attempt that I like the most that I got on for this airplane here. You can take a look at a previous attempt. So this one, it did have the radius that gets bigger towards the trailing edge, but it didn't have so underneath I just sort of filled in all that space, and the airflow, I mean, I would imagine this wouldn't be as good because the airflow kind of comes in and makes an abrupt change in angle underneath the fuselage. So all this one is in the segments of OML is loft just from one arc to another that's a double tangent arc, and nothing underneath. So I mean, we could even imagine not having any fillet, and I mean, in that case we could actually construct the aircraft with this gap here, and I mean, the airplane would still fly. It would just have a bit of interference drag and vortex things going on under here. So I mean, the airplane's still going to work. It's just in your design, it's going to be its own case about trying to blend any gaps you have, any sharp angles between the surfaces to smooth out that airflow. So I'm going to show how I improved from this one initially to, I'm going to show how I modeled this one here. So what that looks like, I tried a few things here. So what I ended up going with was, I believe it's this one. Yeah, this is the one that I ended up going with. So the various things that I tried was, there's a tilted plane inside the fuselage, just offset into it by a small amount. And I looked for flat airfoils, like airfoils that have a really flat bottom section. So if we look at this sketch, this is an airfoil that has a really long flat section to it. And in that sketch, I just, if we look into it, I also intersected the fuselage and sort of moved it around like forwards and upwards until it got to the point where it just barely filled out beyond the outside of the fuselage. So it's within the fuselage, but just barely. I made it wider than that, and it's a not too deep of an airfoil so that it can be longer, go past the trailing edge of the wing root and forwards of the wing leading edge just a little bit without being way far outside the fuselage. So, and from there, what I wanted was, so I tried a few things. I definitely wanted it to be the surfacing to be tangent to the wing, especially from this angle to be tangent, so the airflow is smooth around there. And I wanted an approximately straight line from the side view and approximately tangent from the top view too. So I did a few things with same type of deal with extruded surfaces like that, and then 3D intersection curves. What I found worked the best in the end was to make a plane. So, well, first to draw the wing root tangents, which are just tangent to the trailing edge sketch, 3D curves from the wing. And same thing in the front. Those are tangent to the trailing edge sketches. And these are 3D sketches, so just draw a line and make it tangent. You have to go and visualize these in the wing. So we'd have to go visualize the trailing edge and get it to be tangent to it. So then from there we have a straight line that's tangent and a straight line that's tangent. And we also have these points of the tip of the airfoil, the trailing edge tip and the leading edge tip of the airfoil that's inside the fuselage. And so what I did there, get out of the 3D sketch, is, so there's a loft from that flat-ish airfoil to the root airfoil, and it's guided by, so there's one sketch along the right plane with some pierced points on either airfoil. Then there's also this sketch, which is on a plane. So that's on plane 31, which is a plane that goes through the line that's tangent to the trailing edge at the root and the trailing edge point of that airfoil. So a line and a point will determine a plane. Same thing on the front. So if we go look at, that was plane 31, if we go look at this, that's how it's defined. Same thing with this one out here. Same concept. And that's all that this one is here. And in the end, what that does is, so for a low wing, there really is quite a drop in where your trailing edge is compared to where your fuselage is often, especially for a big chord. That's why I'm actually going to change this design probably to a mid-wing. Saves a lot of space in the fuselage, but you can see how much of a distance the trailing edge is lower than the fuselage. So what this does is streamlines that airflow in a way that it can go through the fuselage and also over the top of the wing and meet at pretty much the same angle anywhere along this span here. So that's pretty much it for the OML of the outer surfacing. But now, if we look at, so I was talking about in the wing, that measurement here. So if we go back to the wing, so if we go back to the tip airfoil sketch, now in there I have a driven dimension measurement of the midpoint of the deepest section of the airfoil here at the, I think it was the 30% chord. And that is measured against a point that's piercing the dihedral layout, just to make sure that, so the root airfoil had that midpoint forced onto this line. The tip airfoil is not actually forced to be on that line, but it ends up being, I adjusted the tip dimension at the tip AOI sketch there, that 0.77, so that it aimed it in the end to pass right through that point. So if we go and take a look at the tip AOI, tip airfoil, and then this one here, this 0.77, if this was different, let's say 0.3, or if it was right on there, because it's an elliptical wing going to a point, it's not the same as in a straight tapered wing where you're absolutely sure that along the whole length of the span, that midpoint is going to be the same, like directly through a line or that type of thing. So if we now look at the tip airfoil, now we can see that actually the midsection, the midpoint of that airfoil is higher up than the dihedral plane. So that's the kind of thing where if you have a spar in the middle of the root airfoil, by the time it ends up getting out here, it's sort of on the lower portion of this tip airfoil. And I mean, you can do that, but we'd rather everything be set up perpendicular for the structure, so that we don't have to adjust for sort of a weird lofting with our structure. So let's take a look at that structure now too, because in parallel to this surfacing is the surfacing of the structure of the wing, the wing box. And I mean, this the design intent for getting this to be 0 is partially for that purpose. So let's take a look at the structural OML now. That's a separate part, but fed with information from the surfacing and sort of iteratively worked on with that to get something that works nicely. Let's take a look at that. So I went back and reset the wing tip airfoil to be directly along that dihedral plane, or the dihedral line. So now let's take a look at the surfacing OML. So that's a separate surfacing part that's taking references from, so for instance, these lines, if we open it up on its own, it's taking, these lines are intersections of the surface of the wing itself. It's taking that information to help design a beam, sort of the outer surface of a beam, to reference later on for the actual parts that will make up that wing box. And here what we're going for, well, I was going for a beam that filled up close to as much depth as it could in the deepest part of the wing, so from maybe like 20% chord back to like 40 or something like that. And I wanted it to be easy to build also, so from the back, the beam is actually, if we open it up, from the back view, it's actually a straight line on the top and a straight line on the bottom. So it continuously converges as a tapered beam. Well, what that would mean for the root is just to set that angle initially, and then the spar caps can just be straight the entire length, which is easier to manufacture. From the top, if you have so this portion is also, the front one is straight, parallel to parallel to a front plane, and the inboard section of the spar from the back is also parallel to a front plane, but the part that tapers starts a little farther outwards, and that part tapers to a point here. So the reason for doing that, instead of having the taper go all the way to the inside, is at that point you have a compound cut. You have an angle, in this case 3 degrees from perpendicular to its face, so 3 degrees here, plus the 5 degrees of the dihedral, and then that's meeting that, so that's 2 different angles meeting in one point, and then that's kind of a complex meeting of geometry where you've got angles in 2 different planes both happening in one point. I'd rather that, so here I had the tapering stop at one point, and the tapering from in the top plane stop at one point, and the tapering from the back point start from a different point back in here, so that there's no compound cut. So if we take a look at the OML, so if we go to normal to that surface, what we can see is there's an abrupt change in angle here, not in the front, but there's an abrupt change in angle at one point here. But then if we go normal to this, it's straight the entire way. So that's what I was going for, just to break up the changes in angle of the spars into different areas of the structure, so that different fittings can just have one change in angle to deal with and not changes in angles in 2 different planes. So, and what this is doing is taking information from the intersections of the surface of the wing surfacing, and well, there's 4 of those because we want to track that along near where the spars are going to be, just to have about the same amount of clearance on all four corners of that beam to maximize the size of that beam. So yeah, that just involved finding out in the tip, getting the sort of a midpoint of where the average of these four endpoints of intersection happen along the intended planes of the spar, and same thing at the root, and then drafting a line between those two midpoints, and that should be approximately the wing planform plane, but it won't be exactly because the structure has its own constraints, this 3-degree angle and the angle of that plane and everything. So there's a separate planform plane that gets created inside the structure that's not exactly the same as the actual planform of that dihedral at 5-degree plane for the surfacing, but it's just here for maximizing sort of the depth of the spar, so that we have at least enough clearance for ribs to be placed around the spar all around its four corners. So that's the structure, and the way that is referenced later on. Let's untransparent it. So the way that this is referenced later on for the subassemblies will be used to create the actual parts, the fittings that make these structural angle changes, and sort of the sheet that creates the wing skin, and the in this case I'm going to use angles as the spar caps. So that's it for the OML structure, and well, yeah, the intention here was for it to meet in the keel beam that could house payload just underneath all the passengers. That was the intention here, for the wing box to meet this keel beam in a way that it doesn't the loads kind of intersect all at the same point in here. And then there's going to be some fittings, some frames that take care of all that load and give some space for cargo in here, and allow the wing loads to go around the keel beam, and the keel beam loads to pass by that wing box, and in a way that it's all kind of meeting in the same area here. So that was a design intent, and this does that design intent. But looking at it later on, I'm thinking that just the size that required to make the fuselage, I don't think this surfacing in the end is going to be filled up in an efficient way by all the parts that need to be in there. I mean, it's sort of the fuselage ended up being bigger than necessary, and the wing root fairing you can see is way low. I think I'm going to change this design to be a mid-wing configuration, actually, where I'm going to go into the dihedral layout and raise that would be this dimension here, raise the wing upwards, and what that'll do is so I didn't want to do it right now, but there it's trying. So the wing box will meet, and there you can see that I just changed this by accident, and the whole surfacing did update on its own. So this dimension drives quite a bit of the wing and the wing root fillet and all that. So what I'm gonna do probably later is raise the wing so that it's a mid-wing configuration, and tilt this airfoil for the wing root fillet back to being straight, in the right plane, so that it comes out straight. And then this bar will kind of meet up with the plane where the passengers are. So, I mean, if we take a look at this, and let's hide the surfacing. So this beam is going to come in and meet, instead of just below where the passengers are, and it wasn't interfering before, I just accidentally moved everything up a bit, but I'm going to move it up a few inches so that the beam actually does meet where the passengers are, and that will allow for a smaller fuselage, like all this space that I don't think there's enough that needs to be put into the aircraft that could fill up all that space. So the fuselage will be less high, it'll be a less deep fuselage. And this beam will be brought up. The only thing at that point is that these passengers can't be within the keel beam or partially within it. So what's going to happen is there's going to need to be some frames that have the top skin and the caps end here, and that curve that top forces up and over and around to the other side for the top skin, and the bottom can probably clear underneath and just go straight across like it does right now. The wing skin just goes straight across. Here right now the top wing skin just goes straight across, really light, really efficient, but it's kind of forcing the rest of the aircraft to be a little less efficient. So that's what I'm going to do, is going to raise this whole beam up and then curve the wing top skin up and over the top, and have a sort of a beefy frame that has a cutout for all the passengers to have sort of a tunnel that they exist in for that 4 inches of fuselage stations here. So that's how you can see kind of how the design intent of the top level can influence surfacing downstream of that, and then the bottom level parts, for instance the ribs and the structure, can follow from that by referring to it and taking geometry from it, and then also editing and having it have its own geometry that is not coming directly from the references. Not every single geometrical piece of the part is coming directly from the references, but a few key, for instance, like for this part here, a few lines from the structure OML could be taken in and used to generate that part. And if actually we can take a look at, I had started that curved design in another aircraft, so let's take a look at that. So this is actually one of the this is the original version of this aircraft that was a mid-wing, and I think I'll probably go back to that in the version in the version that I was working on there. I mean, this one has other things in it that aren't done as well, like the wing root fillet. I mean, this isn't actually how a wing root fillet would be. You could make it like that, but it's not exactly what you'd want. And the way that I attached these back spars was not exactly like welding a piece like that. I don't think it would actually work all that well. But the overall concept of this frame in the front that has a tunnel for the passengers that allows the wing skin. Well, there's no wing skin that goes all the way across in this design, but that would be the way to do it. Would be to have this wing skin be able to curve up and over the top, and have the passengers have a continuous tunnel they can exist in. So this part here, if we go to the fuselage, and it's this part here. So if we open that part takes in information from the surfacing. Just a few things, like, well, the passengers themselves, I guess they're part of the surfacing, and the structural OML. And then this is just one single one part that just uses some references from the top. So that's how it would be. So anyway, all that to say that the surfacing can sort of lead the way for your conceptual design of the major parts and connecting interfaces in tandem with the aircraft shape. So let's go back to the point here that we have the segments of the OML for the overall aircraft, but they're overlapping, like in here with between the wing and the fuselage. They're overlapping and they have gaps, for instance, back here. So how do we combine those to make the surfacing at the subassembly level, which we're actually going to use to reference for parts? So that, for instance, you can see the subassembly of the fuselage with some of the initial conceptual design of the parts, the major connections. That one does not have overlap or gaps. This OML is actually what the final construction will look like once the frames are use a reference of the surface for that. For instance, like lower frames and then hatch frames above that. And so yeah, let's recreate the surfacing for a subassembly. So let's do the fuselage. So let's pretend that we don't have one yet for the fuselage. So we just have these two so far in our aircraft design. So first we're going to insert a new assembly. That's going to be our fuselage. We'll mate that into position so it's constrained. Then we'll put a new part in it and float it and get that one into position. So this is going to be our OML. So that's the OML that we're going to refer to for parts within the fuselage subassembly. So we'll go and edit it directly. And first we'll just take in some of the surfacing from the overall segments of surfacing from the overall OML of the aircraft. So that's going to be in surfaces, so we're going to use an offset surface and just grab some of these, the faces that we need. That's going to make the overall fuselage without the wing. And notice here we're going to put 0 inches, and as soon as we enter that in, it changes from offset to copy. So we're really just copying in the surface into a new part here. And then other than that, we're also going to need the wing. So we'll do another offset surface of, we won't need the winglet all the way out here, but we'll need these faces here. So there we've got most of what we need so far. We're also going to need the plane that cuts. We're going to cut the fuselage right where the OML of the structure changes angle here. So we'll need that as a reference. So that's going to be in here. I believe it's in the wing. Be actually in the structure. Yeah, that's going to be in the structural OML. Here it is. So we'll make a plane that is coincident to that plane. We're just copying it in. Okay. So now we can edit directly in this part. We'll have a lot less going on. So we have 7 surface bodies here. First, we're going to knit these together. So let's just grab these actually from above here and knit together. So now we just have this one fuselage cone or cylinder. Then we have the wing, and we can knit those together as well. We have this plane. May as well start by chopping off what we don't need here, so we can trim. Let's trim this surface. The trim tool is going to be the plane, and we're going to keep this section here. So that's going to be the fuselage. We need to mirror all of this. So let's take this and mirror it. From the right plane. Now we still have, if we look in here, there's still quite a bit of overlap between these two. So we need to trim and just keep the surfacing that we need. Otherwise later we're going to, if we keep these three surfaces separate and start making frames off of this, we're going to end up with there's going to be extra lines. We're going to have to be trimming constantly. Yeah, we want to just have one nice surface that we can deal with. So for now, let's hide this. And what I'm actually going to do is make a 3D sketch and just copy in that root of the wing fillet, the root fillet. Let's make another one for the other side. So 3D sketch, grab these two, and from here to here, let's make a lofted surface. So that's going to sort of close sort of the wings portion. And we should knit all these three together. So now we just have two surfaces that we can use for a mutual trim now. So what that is, let's take a look at this. This is pretty neat. So I go to trim, and instead of like using the plane and just chopping, using one feature as a cut and the other feature as what is being cut, this is going to be a mutual trim. So we're going to start it with these two bodies, and we can either keep or remove sections, and as you select things they disappear. So there are sections inside these inside what's displayed here within it that we can't actually see. So in this case I'm going to use keep selections, and for instance we know that we're going to keep this part and these two parts, and then we can see what's being cut away from inside. So that does look like we're not going to keep this part. There's a lower part of the fuselage than that, you can see. And these parts are obviously where the wing root fillet meets the fuselage. So that should be good. We can just press OK and then take a look at it. So you can look at it from inside, and now I believe, so we do have only one surface now. We can take a look, for instance, with a section view. That looks good. So that's how you can do. Now we have one surface to reference the fuselage from. And if we go take a look at the actual one, look at the actual finished one, that's pretty much what it was. It also has this split line, So yeah, we can just take a look at that, how have these, this is useful to have because if you take a, let's say we're doing a frame over here and the upper frame is going to be a different assembly of a hatch, and the lower frame is going to be more permanent, attached to the keel beam. It's nice to have them as two separate surfaces, so the intersection has a point between where there's different line segments. So let's just do that part too. And yeah, there's also, I mean, there's a cut of the tail boom, the last bit of the tail cone. But let's just take a look at the split line. So for that, we need to be editing it in here. So let's close it here. Edit it in here. And we just need the actual reference of the split line. So it's going to be from here, I believe in the fuselage. That's the one. So we'll just copy it in, sort of feed it downstream into the subassemblies, and then go in here. So we have this single surface. We want to get a second surface where the hatch is at, which doesn't exactly correspond to where the surface faces transition. So let's use this as, we can input a, what is it, a split line. So the faces that it's going to cut, well, we can choose the entire, okay, we actually have to choose faces. So let's just choose them all actually. And what that does is, it's still only one surface. It just kind of split them across. So if you want them to be two different colors, I mean, this would be enough for just having a separation between line segments in the intersection of surfaces. But yeah, if you want them to be two different colors, then what I did was from here, I did an offset surface of just the hatch portions and put this at 0 inches. So there we have a second surface there. And I mean, you can make another offset and just choose the other ones, or you can also hide this one and use delete face. I was using that to get rid of these and then show it again. And now here we can go and let's say we can, in the assembly or in the part itself, might want to have one color for the hatch and one color for the rest of the OML. And you have two different surfaces. So, oh, we actually chose too many surfaces for that split line. Let's go back here and edit it. So, just choose the ones we need. That's it. There we go. be cut by it too. So that's it. This OML is ready to be used by the parts like this one was. And I mean, yeah, the actual structural parts like this can be mated into position on the structural OML. Once you start making frames, like for instance, I mean, we can do, let's insert a new part. Let's say do top to top. Right to right. And front. You wouldn't actually use a distance mate, you'd probably have a layout, but I mean, for now, let's just put one in. For instance, right here. Then we could edit it. And take the intersection. We can also take for reference, let's take that same sketch, hide this. That same sketch can take, for instance, what the intersection here. Take the silhouette actually, so that, because if we take the intersection, it's going to be a bit smaller. We want to take the silhouette, which is the biggest portion of it. For instance, if we take intersection or silhouette. Then usually I would keep the external references to a separate sketch and actually make this all construction geometry. Then we can make a sketch of how the actual frame will look like. So, I mean, one of the frames is going to be the lower part, and it's going to have to support the way these passengers are supported. They might have a floor. The other one's going to have to, for instance, let's do the top one. So we would take this. Maybe make something like that. Maybe we could make offset. Something like that. Now, if we actually want this frame to hold these down, maybe we'll actually reference the intersection curve. If we put this frame farther forwards where it's on top of these, the highest point, then it would, the silhouette and intersection would be the same. But here, let's just take this portion here. And I would probably do this in several steps of sketches instead of, so that you have a, like instead of, here I'm going to trim, but really I would rather, before trimming, maybe keep this sketch and make another sketch that copies it and trim after that. But for now, let's just... Oops. Make this construction. There we go, like that. Something like that. Obviously it doesn't have the whole rest of the details in there, but I mean, that's the concept of how you can use the OML. So where did our surfaces go? There. And then as you're designing these parts, I mean, what I would do is hide their sketches. And so that's the concept of how to do it. How to do it fast and efficiently. We'll cover ways to use shortcuts and things that can help you, like copy with mates or pack and goes while you're inserting multiple assemblies, little sub-assemblies that can to do that faster, to fill up your OML with frames and with to fill up your wing with ribs, things like that. But yeah, for now, that's the concept of surfacing.